Start பண்ணிடலாம்ப்பா. ஓகேங்களா? Last class we have seen about the stage velocity triangle. Okay, we have discussed about the stage velocity triangle, and in this session we will be seeing about the static pressure rise. Okay, we will be seeing about the static pressure rise. Now, the main function of the compressor is to raise the static pressure of the air or the gas. That is, the main function of the compressor is to raise the static pressure of the air or gas which is flowing through it. Okay, this is the main function of a compressor. And the static pressure rise is in the stage depends on the flow geometry and the speed of the rotor. Okay, and the rise in the static pressure will be depending upon the flow geometry and the speed of the rotor. Depending on the both the parameters, the static pressure will rise. That is, it will depend upon the flow geometry and the speed of the rotor. The total static pressure rise across the stage is the sum of static pressure rise in the rotor and diffuser. That is, the total static pressure rise. Okay, the entire static pressure rise in the stages will be the sum of static pressure rise in the rotor and the static pressure rise in the diffuser. So first we have to separately derive the equation for rotor and the stator, and then it will give the, on adding, it will be giving the total static pressure. Therefore, the total static pressure across the stages will be the sum of static pressure rise in the rotor and diffuser. Okay, therefore the combination of sum of static pressure rise in the stator and rotor will give the total static pressure rise in the stage. Okay, now for this, the expression for these values are derived here by assuming reversible adiabatic process. That is, we have considered it as a reversible adiabatic process. Reversible adiabatic process in the sense it is an isentropic process. We are considering it as an isentropic process, and the constant axial velocity through the stage. We are having two assumptions. One is that it is considered to be as an reversible adiabatic process. One is considered to be as an reversible adiabatic process, and another one is a constant axial velocity. We are considering these two conditions. If the axial velocity is kept constant, then the value of Cx1 will be equal to Cx2 will be equal to Cx3, and this will be equal to Cx. Okay, this condition we have already seen while deriving the stage velocity triangle. Therefore, we are considering two conditions. That is, one, it is a reversible adiabatic process, which is nothing but an isentropic process, and the next one is a constant axial velocity throughout the stage. That means at the inlet guide vanes, at the stage of inlet guide vane, then on the impeller, then on the diffuser, throughout the session we will be considering a constant axial velocity. Therefore, Cx1 will be equal to Cx2, which will be equal to Cx3, and that will be equal to Cx. So we have two assumptions. One is it is a reversible adiabatic flow and constant axial velocity. Okay, we are considering this both condition. Further, in the view of small pressure rise over the blade rows of an axial compressor stage, the flow is assumed incompressible. That is, there will be only a small pressure rise over the blade of the row of the axial compressor. In the rows of the axial compressor, there will be only a small rise in pressure. Therefore, the flow is assumed to be considered as incompressible. Therefore, the density is constant. Therefore, the density is kept constant. Therefore, we are considering three assumptions. One, it is an isentropic process, that is a reversible adiabatic process. Second, it is a constant axial velocity. We are considering the axial velocity as constant, which is Cx. And the third one is it is an incompressible, that is density remains constant. We are considering these three conditions for deriving the static pressure rise. Okay. Now, the Bernoulli equation across the rotor blade rows gives, that is, we are considering Bernoulli's equation to derive this static pressure rise. Therefore, the Bernoulli's equation, as we studied in the fluid mechanics, gives P1 plus 1 by 2 rho of W1 square, which is equal to P2 plus 1 by 2 rho W2 square. Okay, this is the Bernoulli equation where P1 and P2 are the pressure at the inlet and exit at the state 1 and state 2, and W1 and W2 are the relative velocity at the state point 1 and state point 2, where rho is the density. Okay, this is the Bernoulli's equation. Okay, now from this, that is from this Bernoulli's equation, the static pressure rise, that is the static pressure rise, the static pressure rise, that is delta P of R. Okay, where this R denotes rotor, Okay, static pressure rise, this del P is nothing but the static pressure rise of R denotes the rotor. Okay, will be equal to P2 minus P1. Okay, the pressure difference of P2 minus P1. This is the rotor. Okay, this is the rotor section, and this is stage 1 and stage 2. The pressure will rise from stage 1 to stage 2. Therefore, the difference of P2 minus P1 will gives the value of static pressure rise in the rotor. Okay, therefore, delta P of R will be equal to P2 minus P1. Okay, which will be equal to 1 by 2 times rho into W1 square minus W2 square. Okay, consider this as equation number 17. That is, from Bernoulli's equation, we have P1 plus half rho W1 square, which is equal to P2 plus half rho W2 square. We have taken P2 minus P1, and this equation comes on the other side, will gives the value of 1 by 2 rho times W1 square minus W2 square. This is how this equation has arrived. Okay, this we have written from the Bernoulli's equation, that is the static pressure rise in the rotor will be equal to P2 minus P1, which is equal to 1 by 2 rho times W1 square minus W2 square. Now from the velocity triangle, from the velocity triangle, you can see this is the velocity triangle. Okay, this is the velocity triangle. In this inlet velocity triangle, you can take an equation W1 square, that is, this is the hypotenuse, where W1 square will be equal to Cx1 square plus Wy1 square. As per Pythagoras theorem, we can take W1 square is equal to Cx1 square by plus W1 square. Okay, this equation we can take. Therefore, from the velocity triangle, W1 square will be equal to Cx1 square plus Wy1 square. This is as per Pythagoras theorem from the inlet velocity triangle. From the inlet velocity triangle, we have taken W1 square is equal to Cx1 square plus Wy1 square. In the same way, you can, in the exit velocity triangle, you can take W2 square is equal to Cx square plus Wy square. You can take this equation W2 square from this exit velocity triangle. Okay, therefore, from the exit velocity triangle, you can take W1 square is equal to Cx2 square plus Wy2 square. Okay, this two equation has been taken from the corresponding velocity triangle, that is from inlet and the outlet. Now combining this equation, this is 2. Okay, this is 2. Now combining this two equation and writing in this form, that is W1 square minus W2 square, writing in this form, the equation can be rearranged as W1 square minus W2 square will be equal to Cx1 square plus Wy1 square minus Cx2 square minus Wy2 square. Okay. When we multiply minus sign on this, it will become minus Cx2 square and minus Wy2 square. Therefore, this equation is being written in this form. We know that we have made an assumption that the axial velocity is constant. We have made an assumption that the axial velocity is constant. Therefore, we know that Cx1 is equal to Cx2 is equal to Cx3 will be equal to C of x. We have made this assumption. Okay. From this equation, in this equation, the Cx1 square and Cx2 square will get cancelled out. Since this both are equal, it has a minus sign and it has a positive sign. Therefore, this two parameter gets cancelled out, and W1 square minus W2 square will be equal to Wy1 square minus Wy2 square. Okay. Therefore, this equation will take a form of W1 square minus W2 square will be equal to Wy1 square minus Wy2 square. Okay, it will take this form. That is, since we are considering the axial velocity as constant, the above equation will take a form like this: W1 square minus W2 square is equal to Wy1 square minus Wy2 square. Now from the equation which we have derived yesterday, that is from 12a and b, that is 12a and 12b equation, which gives, that is the equation number 12a gives, this is 12a, this equation gives Cy2 minus Cy1 will be equal to Wy1 minus Wy2. Okay, this is the equation number 12a. In the same way, the equation number 12b, which we have derived yesterday, will give equation of Cx tan alpha 2 minus tan alpha 1, which will be equal to Cx into tan beta 1 minus tan beta 2. Okay, this two equation we have derived when we are solving the stage velocity triangle. Okay, this two equation we have derived yesterday, and from this two equation you can write, that is the value of W1 square minus W2 square. This equation can be rewritten in such a way that the value of W1 square, minus W2 square will be equal to Cx square into tan beta 1, that is tan square beta 1 minus tan square beta 2. Okay, you can write this equation in this form. Okay, that is the value of, actually you have to take this value W1 square minus W2 square will be of this form: Cx into tan beta 1 minus tan beta 2. On squaring this, you will be getting Cx square into tan square beta 1 minus tan square beta 2. Okay, therefore W1 square is equal to minus W2 square is equal to Wy1 square minus Wy2 square. We have taken this equation in a form of this. Okay, we have replaced this by this equation. Okay, therefore the equation W1 square minus W2 square is equal to Cx square into tan square beta 1 minus tan square beta 2. This is how we have arrived this equation. Okay, the equation, this above equation, when you substitute on the equation number 17, that is this equation W1 square minus W2 square, when substitute on this equation number 17, you will get an equation of a form. The above equation when substituted in equation 17, we will get delta P of R. That is, this is the equation number 17, which states that static pressure rise in the rotor is equal to P2 minus P1, which is equal to half rho into W1 square minus W2 square. We are replacing this W1 square minus W2 square by this equation. Okay, therefore the equation will take a form delta PR is equal to 1 by 2 times rho into Cx square into tan square beta 1 minus tan square beta 2. Okay, this W1 square minus W2 square has been substituted in the equation number 17, and you will be getting this equation. And consider this equation as equation number 18. Consider this as an equation number 18. Now, in the similar fashion, if you substitute the parameters for the diffuser, that is, this is the diffuser section. Okay, that is from 2 to 3. Okay, we have taken the static pressure rise. We have derived the static pressure rise in the rotor, that is delta P of R, that is from stage 1 to stage 2. Now, if you proceed the similar equation in the same fashion, you can also get an equation for the diffuser, that is from this section 2 to 3, that is from stage 2 to 3, you can get the equation for diffuser. Since, as we have already seen, the total static pressure rise across the stage is the sum of static pressure rise in the rotor and diffuser. Okay, the stage where the rotor is at, this is the rotor stage, that is from 1 to 2, and this is the diffuser stage from 2 to 3. We have derived the equation, or we have obtained the equation for 1 to 2, that is from stage 1 and 2. Now we have to derive an equation in order to find the static pressure rise in the diffuser. So we will be considering the stage 2 and 3 for deriving the expression of static pressure rise in the diffuser. Okay, we will be following the same procedure and we will be deriving the equation. So if you follow the equation similarly, the Bernoulli's equation across the diffuser blade rho gives, that is, this is the diffuser blade. Okay, this is the diffuser blade. Okay, this is the diffuser blade. Therefore, the static pressure rise across this diffuser blade will also follows the same procedure as we have derived for this rotor blade. Okay, therefore, from this, the value of delta P of D, where delta P is the static pressure rise and D denotes the diffuser. Okay, and D denotes the diffuser. It will be equal to P3 minus P2. That is, this is the stage 3 and this is stage 2. The difference in the stage pressure at the stage 3 and stage 2 will give the static pressure rise in the diffuser blade. Therefore, delta P of D will be equal to P3 minus P2. And again, this equation can be written as 1 by 2 times rho into C2 square minus C3 square. In the rotor, we have considered as a relative velocity. Therefore, we have used W1 and W2 as the velocity component. But in the diffuser, we will be using the absolute velocity across the diffuser blade. Therefore, we are considering as the velocity as C2 square minus C3 square. And consider this equation as equation number 19. Consider this as an equation number 19. Now, this equation in the same fashion as we derived here, okay, can be written as, that is, we have taken W1 square minus W2 square as WY1 square minus WY2 square. If we have taken this equation in the same fashion, this equation can also be written as delta P of D will be equal to 1 by 2 times rho into Cy2 square minus Cy3 square. That is, in this case, we have taken the difference in the relative velocity as W1 square minus WY2 squares. This 1 and 2 is the stage 1 and stage 2. Okay. This 1 denotes the stage 1 and 2 denotes the stage 2. But in the diffuser section, the stages involved are 2 and 3. Therefore, we are using this 2 and 3. This is stage 2 and stage 3 for the diffuser section. Therefore, delta P of D will be equal to 1 by 2 times rho into Cy square minus Cy3 square. Okay, this equation has been arrived. Now, this equation can be written in a form delta P of D will be equal to 1 by 2 times rho into Cx square into tan square alpha 2 minus tan square alpha 3. Again, since we have taken this from equation 12a and 12b, considering equation number 12a and 12b, we have rearranged this equation. Okay, we have rearranged this equation. That is, after substituting in the equation number 12, we have arrived at an equation which states that W1 square minus W2 is equal to Cx square into tan square beta minus tan square beta 2. In the same way, we have taken this equation for Cy square minus Cy1 square. Therefore, Cy2 minus Cy1 will be equal to Cx into tan alpha 2 minus tan alpha 1. We have used this equation. That is, we have considered both the equation and we have rewritten this equation. That is, Cy2 square minus Cy3 square is being written as tan square alpha 2 minus tan square alpha 3. That is, this equation has been framed. Okay. Now, if you assume, that is, assuming alpha 3 is equal to alpha 1. Okay, assuming alpha 3 is equal to alpha 1. Assuming alpha 3 is equal to alpha 1, the above equation can be written as delta P of D will be equal to 1 by 2 rho Cx square into tan square alpha 2 minus tan square alpha 1. Okay, now consider this equation as equation number 20. In this equation, we have considered as alpha 3 is equal to alpha 1 by considering that this alpha 3 has been replaced as alpha 1. We have just made an assumption that the angle alpha 1 is equal to angle alpha 3. That is, this angle is the alpha 1 and this is alpha 3. Definitely this will be equal. Okay, according to geometry, this will be equal. But we are assuming that this alpha 1 will be equal to this alpha 3, and by considering that you will be getting the static pressure rise in the diffuser will be equal to 1 by 2 times the rho Cx square into tan square alpha 2 minus tan square alpha 1. We have derived this equation. Now the stage pressure rise. Now the stage pressure rise in the diffuser. The stage pressure rise is P3 minus P1. That is, we are considering from stage 1 to stage 3. Okay, in between there will be a rotor and diffuser. We are considering from stage 1 to stage 3. We are considering from stage 1. That is, from stage 1 to stage 3. This will give the total static pressure rise. That is, it comprises of this rotor blade and the diffuser blade. Therefore, the total static pressure will be P3 minus P1. This will give the total static pressure rise. Okay. Therefore, P3 minus P1 will be equal to delta P of stage. This ST denotes the stage. Okay. The ST denotes the stage, which will be equal to delta P of R plus delta P of D. Delta P of R plus delta P of D. That is, as we have already seen, that total static pressure will be equal to the summation of the static pressure rise in the rotor and the static pressure rise in the diffuser. Therefore, we will be getting this equation. Now, substituting from equation 18 and 19. From equation 18 and 19, that is, the equation number 18 is delta P of R. This is the static pressure rise in the rotor. This is the static pressure rise in the rotor. And the equation 19 is the static pressure rise in the diffuser. This is the static pressure rise in the diffuser. That is the equation number. Take this equation as equation number 20. Okay. This is equation number 20. Okay. From this, you can write delta P at the stage will be equal to 1 by 2 rho times Cx square into tan square beta 1 minus tan square beta 2 plus tan square alpha 2 minus tan square alpha 1. Okay, we have made a summation of the rotor and the diffuser. This is the equation number 18 and this is the equation number 20. By combining this, by adding this to equation, you will be getting this equation. That is, we have taken 1 by 2 rho times Cx square as common, and you will be getting tan square beta 1 minus tan square beta 2 plus tan square alpha 2 minus tan square alpha 1. Okay, you will be getting this equation. Now, if you expand this equation, okay, now if we expand this equation, that is, we will be just considering a square minus b square is equal to ab into a minus b. We will be a plus b into a minus b. We will be considering that expression in order to expand this equation. Okay, by using that relation, if you expand this, delta P at the stage will be equal to 1 by 2 times the rho into Cx square. We are taking Cx square inside. Okay, Cx square into this tan square beta 1 minus tan square beta 2 will be equal to tan beta 1 plus tan beta 2 into tan beta 1 minus tan beta 2. Okay, this equation has been expanded as tan beta 1 plus tan beta 2 into tan beta 1 minus tan beta 2. We have expand this equation in this form. Again, this equation will take a form plus when you multiply cx square in this equation, this 2 will get cx square and this 2 will get cx square. Therefore, this cx square can be written as cx into tan alpha 2 plus tan alpha 1 into cx into tan alpha 2 plus tan alpha 1 into cx into tan alpha 2 minus tan alpha 1. Okay, we will be writing this equation in this form. That is, we have taken cx into tan alpha 2 plus tan alpha 1 and cx into tan alpha 2 minus tan alpha 1. Okay, for mathematical convenience, we have written in this form. Okay, now this stage pressure rise, that is the pressure rise in the stage, will be equal to 1 by 2 times rho into, in this equation, okay, in this equation, if you take cx tan beta 1 minus tan beta 2 as common, you have tan beta 1 minus tan beta 2. Okay, this equation will take a form, that is, we should rearrange this entire equation. Okay, we should rearrange this entire equation and write an equation in such a manner that you will be getting this 1 by 2 times rho cx into tan beta 1 minus tan beta 2 into cx tan beta 1 plus tan beta 2 plus cx into tan alpha 2 plus tan alpha 1. Okay, now this equation, on rearranging this equation on rearrangement, okay, this equation on rearrangement, okay, this equation on rearrangement will give, that is, we will be using two equations, that is equation number 4c and equation number 8c. Okay, we will be using this both equation, that is, we have derived this equation in the last class, which gives u is equal to cx1 into tan alpha 1 plus tan beta 1, and the equation 8c gives u is equal to cx2 into tan alpha 2 plus tan beta 2. Okay, you can write this equation, you can use this equation, and by substituting these values in the above equation, that is the above equation, that is delta P of stage will be equal to 1 by 2 times rho cx into tan beta 1 minus tan beta 2 into cx into tan alpha 1 plus tan beta 1 plus Cx into tan alpha 2 plus tan beta 2. Okay, this is the stage pressure rise equation, and in this equation, this tan alpha 1 plus tan beta 1, this equation can be replaced by this u, and this is also be replaced by the peripheral velocity u. And from the velocity diagram, you can see the peripheral velocity remains constant. That is, u1 is equal to u2, which is equal to u. That is, from this velocity diagram, you can understand that u1 equal to u2 is equal to u. That is, the peripheral velocity is kept constant in the inlet and the outlet velocity triangle. Therefore, the peripheral velocity remains constant. Therefore, this equation will take a form. This equation will take a form delta P at the stage will be equal to 1 by 2 times rho Cx into 2u into tan beta 1 minus tan beta 2. That is, this entire equation and this entire equation is being replaced as u. Okay, this is being replaced as u, and this equation is being replaced as u. Okay, therefore, by adding both the peripheral velocity, you will be getting the value of 2u. Okay, now cancelling this 2, you will be getting delta P, that is the stage pressure rise, will be equal to rho Cx u into tan beta 1 minus tan beta 2, and consider this as an equation number 21. Consider this as an equation number 21. In the same way, this equation can also be written as delta P at the stage will be equal to rho Cx of u into tan alpha 2 minus tan alpha 1, and consider this as equation number 22. That is, we will be combining this both the equation and writing in this form, and this will be equal to the value of u, and therefore we will be considering as 2u, and this 2 will be getting cancelled, and the final equation will take a form of rho Cxu into tan beta 1 minus tan beta 2, and again rho Cxu will be equal to tan alpha 2 minus tan beta 2. Okay, this is how we have arrived this equation. Okay, this is how we have arrived this equation. And for isentropic flow, that is for isentropic flow, for an isentropic flow, change in pressure and enthalpy and work are related by an equation which is delta P at the stage divided by rho, which is equal to delta H of the stage is equal to W. This equation we have already seen in the later classes, that is in the unit number 2 and 3, we have used this equation, but actually this equation has been derived in this corresponding static pressure rise. Okay, therefore you can combine the value of, that is, you can combine the parameters of change in pressure, enthalpy and work by this equation, and by using this equation only we have derived certain equation in the centrifugal compressor centrifugal compressor and the fan and blowers, which we have seen in the unit number 2 and 3. Okay, this is how that equation has been arrived. Okay, therefore the total static pressure rise is given by this two equations, that is equation number 21 and 22. And for an isentropic flow, the change in pressure, enthalpy and works are related by this equation. Okay, do you have any doubt? Do you have any doubt in this derivation? Can I ask a doubt? Dina? Dina or Kingla?
Sir?
Can I have a doubt?
No, sir.
Divakar?
Sir, சொல்லுங்க sir.
Can I have a doubt?
இல்லைங்க sir.
எல்லாம் புரிஞ்சிச்சா?
ஓகே சார்.
புரிஞ்சிச்சா எல்லாம்?
சார் புரியுது சார்.
இதுல நான் ஒரு ஈக்குவேஷன்ல ஒரு இடத்துல நான் ஒரு டேட்டா சொல்லாமே நடத்திருப்பேனே, அது உங்களுக்கு என்னன்னு நோட் பண்ணீங்களா?
எதுங்க சார்?
இந்த பேஜ்லயே ஒரு இடத்துல ஈக்குவேஷன் வந்து நான் அதை எக்ஸ்பிளைன் பண்ணவே இல்லை. ஓகேங்களா, டெலிபரேட்டா விட்டுட்டே போயிருக்கேன். ஓகேவா, அது ஈக்குவேஷன் என்னன்னு சொல்லுங்க. ஸ்ரீஹரி நீங்க சொல்லுங்க. ஸ்ரீஹரி இருக்கீங்களா? எஸ் பாலாஜி? எஸ் பாலாஜி இருக்கீங்களா? தர்ஷன்?
சார் இருக்க சார்.
சொல்லுங்க
சார். தெரியல சார் எதுன்ட்டு.
கவுன்சிங்களா? வேற யார் கவுன்சா? தீபச்சந்திரன்?
சார் சார்
ஆனா அதுல ஒரு ஈக்குவேஷன் வந்து இன்னொரு ஈக்குவேஷன் எக்ஸ்பிளைன் பண்ணாமே நான் வந்து எழுதியிருப்பேன். ஓகேவா?
ஓகே சார். சார் அந்த இதுதாங்க சார், அந்த டெல்டா பிஎஸ்டி. சார் அந்த ஃபர்ஸ்ட் ஈக்குவேஷன் தானுங்க சார்.
எதுப்பா இந்த ஈக்குவேஷனா?
ஈக்குவேஷன் 18 and 20.
ஓகே,
அதுல ஃபர்ஸ்ட் அந்த ஈக்குவேஷன் தானுங்க சார்.
இந்த ஈக்குவேஷன் வந்து நம்ம நார்மலா எடுத்து எழுதுறது தாண்டாக்கண்ணா. இதுல இருந்து இந்த ஈக்குவேஷன் வந்து நம்ம எழுதியிருப்போம்.
ஆமாங்க சார். tan inverse பீட்டா 1ங்கிறதுக்கு பதிலா தான் இந்த tan பீட்டா 1 + tan பீட்டா 2.
சரி, இந்த ஈக்குவேஷன் இருந்து இந்த ஈக்குவேஷன் எழுதியிருக்கோம்ல.
ஆமாங்க சார்.
tan பீட்டா 1 tan பீட்டா 2 வந்து காமனா எடுக்க முடியுமா?
முடியாது சார்.
அப்ப நான் எடுத்துர்க்கனே.
சார் அது வந்து ஃபார்முலா
சொல்லுங்க
சார். ஃபார்முலா தானங்க சார். tan பீட்டா 1 + tan cx tan பீட்டா + பீட்டா 1 + tan பீட்டா 2ங்கிறது தான் அந்த ஈக்குவேஷன் சார். tan பீட்டா 1 + tan பீட்டா 2 * tan பீட்டா 1 - tan பீட்டா 2ங்கிறது.
ஓகேடா, இது ஓகேக்கண்ணா. இந்த இதோட எக்ஸ்பான்ஷன் தான் இது, இதோட எக்ஸ்பான்ஷன் தான் இந்த ஈக்குவேஷன். ஓகேவா? ஓகேவா, இதுல இருந்து நான் tan பீட்டா 1 - tan பீட்டா 2 வந்து நான் காமனா எடுத்திருக்கேன்.
ஆமாங்க சார், வெளியில எடுத்திருக்கீங்க.
ஓகேவா, அது எடுக்க முடியுமா?
tan பீட்டா 1 - 2 இல்லங்க சார், எடுக்க முடியாதுங்க சார்.
அப்ப எப்படி எடுத்திருக்கேன்? எடுத்து தானே சால்வ் பண்ணியிருக்கேன் நானு.
ஆமாங்க சார்.
ஓகேவா, இந்த ஈக்குவேஷன் நான் எப்படி எடுத்தேன்னு நீங்க லாஸ்ட் கிளாஸ் எல்லாத்தையும் பார்த்துட்டு எனக்கு நாளைக்கு சொல்லணும். ஓகேங்களா?
ஓகே சார்.
ஓகேவா, யாரை வேணா நாளைக்கு கேட்பண்டாக்குன்னா நாளைக்கு சொல்லாதவங்களுக்கு வந்து ஆப்சன்ட் மார்க் பண்ணிடுவேன். ஓகேவா, இன்னைக்கே வந்து ஸ்ரீஹரி அண்ட் எஸ் பாலாஜி வந்து நான் ஆப்சன்ட் தான் மார்க் பண்ணுவேன். ஓகேங்களா? நாளைக்கு சொல்லினா நான் மார்க் பண்ண மாட்டேன், நோ ப்ராப்ளம், ஓகேவா? பட் இந்த ஈக்குவேஷன் எப்படி வந்ததுன்னு எனக்கு வந்து நாளைக்கு நீங்க சொல்லணும், ஓகேவா? இந்த ஈக்குவேஷன்ல வந்து tan β1 minus tan β2 வந்து நான் காமனா எடுத்திருக்கேன். எப்படி காமனா எடுத்தேன்? ஏன்னா இந்த பேராமீட்டர்ல வந்து உங்களுக்கு அந்த வேல்யூவே இல்ல, ஓகேவா? பட் ஐ ஹவ் டேக்கன் as tan β1 minus tan β2 as common. எனக்கு இது வந்து நீங்க வந்து எக்ஸ்பிளைன் பண்ணணும், ஓகேங்களா? தீபச்சந்திரன்
சார் கேக்குது சார், எக்ஸ்பிளைன் பண்றேன் சார் நாளைக்கு.
உங்களுக்கு மட்டும் இல்ல, பொதுவா எல்லாத்தையுமே, ஓகேவா? நான் இங்க யார வேணா கேட்பேன், ஓகேங்களா?
ஓகே சார்.
ஓகேப்பா, இந்த கிளாஸ் புரிஞ்சுதா? மத்தபடி எல்லாம்
புரிஞ்சுதுங்க சார்.
சரிங்கண்ணா. நான் உங்களுக்கு இதுல வந்து இன்னும் டாபிக் வந்து இருக்கு, ஓகேவா? இந்த ஒர்க் அண்ட் பிளேட் லோடிங் அண்ட் ஃப்ளோ கோஎஃபிஷியன்ட், ஓகேவா? இந்த கான்செப்ட் வந்து நம்ம நிறைய வாட்டி யூஸ் பண்ணிட்டோம், ஓகேங்களா? இது செகண்ட் யூனிட் அண்ட் தேர்ட் யூனிட்ல வந்து இந்த 5 = W/U2 யூஸ் பண்ணியிருக்கோம். ஃப்ளோ கோஎஃபிஷியன்ட் = CX/Uங்கிறது நம்ம யூஸ் பண்ணியிருக்கோம், ஓகேவா? அண்ட் ஒர்க்கோட ஈக்குவேஷனும் வந்து நம்ம எல்லா இடத்துலையும் யூஸ் பண்ணிட்டோம், ஓகேங்களா? அதனால தான் இந்த டாபிக் வந்து எடுக்கல, நீங்க ஜஸ்ட் நோட் பண்ணிக்கோங்க, ஓகேங்களா? ஆக்சுவலா இதுல வந்து என்ன பண்ணியிருக்காங்கன்னா, ஃபோர்த் யூனிட் தான் வந்து செகண்ட் யூனிட்டா எடுத்திருக்கணும், ஓகேவா? பட் சிலபஸ்ல வந்து அப்படி ஃப்ரேம் பண்ணியிருக்காங்க. அதனால தான் நம்மளுக்கு வந்து சில ஈக்குவேஷன்ஸ்லாம் வந்து நம்ம ஏற்கனவே பார்த்துட்டோம், பட் ஆக்சுவலா அந்த ஈக்குவேஷன்ஸ்லாம் இப்போதான் வருது, ஓகேங்களா? அதனால அதனால தான் இந்த ஒர்க் அண்ட் பிளேட் வந்து நான் வந்து ஜஸ்ட் உங்களுக்கு மட்டும் எழுதியிருக்கேன், நோட்ஸா பார்த்துக்கோங்க. நம்ம வந்து இன்னைய கிளாஸ்ல வந்து ஸ்டாட்டிக் ப்ரெஷரைஸ் வந்து பார்த்தது, ஓகேவா? நாளைக்கு வந்து என்தால்பி அண்ட் என்ட்ரோபி டயக்ராம் பார்த்துடலாம், ஓகே? இல்ல வேற ஏதாவது டவுட் இருக்குங்களா?
சரிங்க சார்.
சரி, ஓகேங்கண்ணா.
அந்த ஈக்குவேஷன் நீங்க நேத்து எடுத்த கிளாஸ்ல இருந்து பார்க்கணுமாங்க சார்?
நான் நேற்றுக்கு எடுத்த இது கிளாஸ்லையும் பார்க்கலாம், அதுக்கு முன்னாடி இருக்க கிளாஸ்லையும் பார்க்கலாம், ஓகேங்களா? மேக்ஸிமம் நேற்று எடுத்த கிளாஸ்ல இருக்கலாம், ஓகேவா? எல்லாமே இன்டர்ரிலேட்டட் தாங்கண்ணா. அந்த 4 யூனிட்டுமே அந்த 2, 3 and 4 வந்து எல்லாமே இன்டர்ரிலேட்டட் தான். எதுலயாவது அந்த ஈக்குவேஷன் வந்து இருக்கும். இல்லையா அந்த ஈக்குவேஷனே ரிசால்வ் பண்ணி பாருங்க, உங்களால கண்டுபிடிக்க முடியுதான்ட்டு, ஓகேவா?
ஓகே சார்.
கிளாஸ்ல வந்து கேட்பேன், ஓகே?
ஓகே.
ஓகேப்பா, நான் வந்து இப்ப சிங்க்ரனஸ் குவிஸ் வந்து அசைன் பண்ணிடுறேன், நீங்க எடுத்துருங்க, ஓகேங்களா?
ஓகே சார்.